A very good morning, dear students. In this video lecture, you will find a very important application of Schrodinger wave equation, which is particle in one-dimensional potential well. On the right side of the screen, you are able to view a Schrodinger wave equation, which is a fundamental expression in quantum mechanics, similar to Newton's law of motion in classical mechanics. Okay, the particle in potential well is also reframed as particle in a box. Now here is a visualization of a particle being trapped inside a box. Now imagine that a particle is being trapped inside the box and the ball is free to move inside a box. Now coming to the walls are so thick in such a way that particle can never escape, particle can never penetrate the barriers. That is, particles are bounded by impenetrable barriers. Now coming to the old theory, that classical mechanics, that says the particle can take any energy values. Okay. Now however, when the potential wall becomes very, very narrow, very, very thin, and when it lies in the range of nanometer, the quantum concept, then the quantum theory comes into play, and it says that particle can have only discrete values, that is, only specific values. So we can say that the energy is quantized. Right? Now on the screen you are able to view the simplest form of potential well, that is one-dimensional potential well. Coming to the box, whose width is from 0 to L. The width of the box is from 0 to L. Look at here. Now here a particle, let's look at a particle. The ball is a particle, or it can be an electron whose mass is taken as m and whose velocity is taken as v, and the particle is being trapped inside one-dimensional potential well whose width varies from 0 and L. Okay, and the particle is free to move, in the sense the particle moves only back and forth, and it hits the wall and it gets bounced back. That is, it is restricted by the impenetrable barriers. Now here is the animated effect of a particle. Look at the particle here. The particle can move back and forth, right, since it is one-dimensional. Now coming to the energy, look at the trajectories made by the ball or a particle. That red color indicates that energy of a particle and blue color indicates the wave function of a particle. Now here the energy appears to be discrete. We have fixed energy for at each and every level, and hence that is the concept of quantum mechanics. The energy is being quantized. Now let's look at the boundary conditions applied to the particle. Since these boundary conditions can significantly simplify the mathematical calculations as we derive for Schrodinger wave equations. Look at the boundary condition here. A particle of mass m is being trapped inside the box, and the particle can never be in a still position, and it keeps on moving back and forth, and it possesses kinetic energy, and potential energy inside the box is equal to 0. And the particle can never come outside, hence at the walls and outside the walls the potential is being taken as infinity at the walls and outside the walls. Here is a term we are familiar with, which is psi, which represents function of a particle, that is position of a particle with respect to time. Now here is a new term, that is a square of psi, that gives you probability of finding a particle, that it gives only the prediction of finding a particle and not the exact location. Now let's move on to the boundary condition at the walls and inside the box. Now coming to inside the box, as a particle exists inside the box and it keeps on moving, we can easily find the particle inside. So the probability is not equal to 0. So when I write the probability not equal to 0, that implies that I can find the particle. The probability is not equal to 0. I can find the particle. And now coming to the width, okay, we have to give the restrictions for the width. Since it is inside the box, here I can write the x lies between 0 and L. The x is nothing but width. The width varies from 0 and L. So within the box, this represents within the box, I can find the particle. So probability is not equal to 0. Now let's look at outside the box and at the walls. The particle can never exist outside the box and at the walls. Hence the probability of finding a particle is also equal to 0. Now coming to the wall restriction, here I can write x is greater than L greater than 0. That is greater than or equal to. That shows at the walls and outside the box, and as well as outside the box. So these are the two important boundary conditions imposed on a particle being trapped inside, which significantly simplifies our mathematical calculations as we go on deriving for Schrodinger wave equation.